Welcome, everyone, to the Memphis Astronomical Society. We meet here every month. We have a QR code. If you have a phone with a camera, you can take a picture of that code, and that'll take you to this web page where you can sign up for our newsletter or to join the Memphis Astronomical Society. If you want to understand why you should spend $25 a year and become a member of the Memphis Astronomical Society, see me after the meeting, or you can look on the back of one of our new handy-dandy little business cards with a complete list of cool things you get for your $25 a year. We have a calendar on our website. By the way, if you go to when you get to this web page, if you click on home or that little icon right there, that'll take you to the main page of our website. And you can also navigate your way to our calendar, which is right there. This is what our calendar looks like. We had a mentoring session Saturday night last that I guess went pretty good. I wasn't able to be there. Excellent. And I don't see anything else on our calendar for the remainder of this month. We have an astrophotography group meeting on Wednesday the 20th at 7 p.m. That's a Zoom-only meeting. And reminder to all that the President's Elite Volunteers Club is going strong. We're getting good results from people responding to the call for bringing telescopes to events and showing up, and actually showing up. So that's working okay. So thank you very much for those members of the President's Elite Volunteers Club. We have some new members this month. Gary Reese, welcome. Stephen Womack, Donald Selheimer, Luis Gonzalez, Nathan Toner, and Daniel Thomas. Is anyone of these? Which one are you? Nathan, welcome to the Memphis Astronomical Society. All right. We have a beautiful, colorful newsletter produced by Steve Wright, our most excellent newsletter publisher and editor. And there's some copies of it up here on the front table if you want to take one home and look at it. You get this by email every month if you're a member. Like I said, we have a very active astrophotography group within our organization. It is a load of people that love to take their telescopes out and take pictures of the night sky. Even people that don't take telescopes out and take pictures of the night sky. We have everybody from just starting out taking pictures through the eyepiece of their telescopes with their cell phones to people with multi-$1,000 rigs set up specifically for that purpose only. So, and then a whole lot of expertise in the image processing business, which when you get into astrophotography, you'll find out real quick that simple snapshots don't yield quite the results that you see in the magazines or from the Hubble Space Telescope. But take a little bit of software and work on them a while, and they look almost as good. We have Memphis Astronomical Society branded stuff. Lots of cool things that you can get with our logo and name on them. The Memphis Astronomical Society doesn't make any money off this, but it is a good way to show your support within the community for our organization and what we do. I think this is where I've got a story to tell. Far be it from me to pass up an opportunity to tell a story that demonstrates the rich heritage of the Memphis Astronomical Society since its inception in 1957. And we have a celebrity with us this evening, and that's what I hope this story gets across to you. I'm going to tell the story. I might not get it right, and that's not really important. What is important is that you're left with a feeling of awe and inspiration. So this is the Memphis' own Liberty Bowl Stadium, and our guest Julie Gaskell's father was the architect for this event, for this facility, and that alone is enough to be important. But what is related to the Memphis Astronomical Society was that he was a member of the Memphis Astronomical Society. He used to pick up Bill Bustler as a kid and drive him to the Memphis Astronomical Society meetings. Bill is our longest term, still alive member of the Memphis Astronomical Society. So he joined when he was 13, and he's still a member. He, Mr. Gaskell, consulted with Bill to do the calculations for where the sun would be and how the shadows would reflect inside the stadium as it was being built. So the Memphis Astronomical Society played a part in designing, in placement of this facility and where it's at. Now, if that's not cool enough, all right, she also drives a Volvo PV544. That alone is worth membership, but there you go. So welcome, Julie Gaskell, and thanks for coming out tonight. I was hoping Bill Bustler would be here, but then he would have corrected me, I'm sure, on my story. So for tonight, we have a great presentation by our own Peter VanWylen, a member in good standing with the Memphis Astronomical Society. I want you to know that's an important thing. So, he will talk to us about orbital mechanics and understanding what it takes to keep things in orbit, much of Isaac Newton's work. So thank you very much, and with that, I'll turn it over to Peter.
I have a few helpers that you guys pass out those handouts. So there's a handout that you may want to grab one of, and there we go. That's great. Thank you. So if you are watching from home, if you're on the Zoom, you'll see in the lower right-hand corner of this slide right here, there's a link to the handout. So I know that watching from home, you get a little bit different experience, but you get a handout too. So just grab that, open it up in a different window, or if you've got a home printer, just print it out. And there's some numbers that you might enjoy looking at. Briefly about myself, when I was a kid, I got really into astronomy in middle school and high school. My parents had a telescope that they got me. I used it throughout high school. I went off to college, and I wasn't an astronomy major, and I sort of left it alone for like 20 years. I don't know how I did that, but I've come back around, all right. And so I went to the 2017 eclipse, was awed by that, and then took another 4 years off, and then started playing with asteroid orbits. And I found my way into it I found that there was this giant public data set called the Pan-STARRS survey database. It's 5 or 6 years of data, and you can just go on and you can tell, I want a picture of this part of the sky on this date, and it'll give you the picture, and you can see if you can find asteroids in the archives. And I was submitting observations, sort of like of a known object that wasn't perfectly known, and if you found some observations, you could improve the orbit. So I kind of got into that, and then slowly I've been diversifying into more just doing lots and lots of orbit work. So I don't do as much of the archive work anymore. I do a lot of orbit work, finding really interesting orbits that are in some way or another exceptional. I have a few people that help with archival stuff that are better at archives, so I might send them an orbit of an interesting object. They might dig in the archives, and we can see if we can together make it get to the bottom of an object that is labeled as an asteroid, but we might think it's a comet, or it might be exceptional in some other way. The reason I love asteroids and comets so much is not comets are beautiful no matter what. Asteroids are rather boring through the eyepiece of a telescope. Asteroid means star-like. That's all it means. It looks like a star. It literally looks exactly like a star in your telescope. But what's beautiful is we can send spacecraft to them. And so while a galaxy, your only shot is through a telescope, when it comes to an asteroid or a comet, you can send spacecraft. So Comet 67P, I think this one maybe was ESA, I can't remember. Yeah, I think that's the European Space Agency went there. Donald Johanson, that's a recent picture. I believe that's the Lucy spacecraft on its way out to the Jupiter Trojans. And then Ceres is the first asteroid that was found. They're all beautiful up close. I really I find the pictures pretty, and I feel like we're probably looking at, in the next 20, 30 years, we're going to get more of these great pictures as it gets cheaper to get out there. Maybe someday we'll be sending CubeSats to get a snapshot of an asteroid, okay? But briefly, I did bring a baby asteroid with me, okay? So is anyone here a good catch? All right, okay, we got one. Okay, ready? It only has one sharp edge. Are you ready? Okay, all right, so thank you. That was an asteroid toss. The path was parabolic, right? Okay. And I have a question for you. How did my baby asteroid, which is actually just a meteorite, okay, how do you think it felt while it was in flight?
Happy.
It was happy, of course it was. Why was it so happy? It was weightless. It was back to its natural state. It spent billions of years in weightlessness, and then it landed in the Sahara Desert, and it was like, this is awkward, okay? And so, literally, for billions of years, it's just falling through space. It's weightlessness, and then, now it sits on my desk, and it is bored silly. So yeah, please pass it around. But I feel like, for that brief 2 seconds while it was in flight, it was back to its natural state of falling through space and experiencing weightlessness. Now, what that brings me to is, what is an orbit? Was this an orbit? No. Although it was close, okay? In a sense, it was just a very, very short suborbital arc, okay? With a little bit of air resistance mixed in, okay? And so, in a sense, it wasn't an orbit because it had an impact only 2 seconds after it was launched. But in another sense, it was being controlled by gravity and gravity alone. During that few seconds, air resistance didn't play a part. And so that's why its experience of flight in this room is very similar to what it experienced for billions of years. And what Kepler said was that an orbit is an elliptical path with a central body at one focus of the ellipse, such that equal areas are covered in equal time periods. Okay, a little bit of a mouthful, but what Kepler got right was an orbit is an ellipse. He figured out the shape, and he figured out how quickly it moves along that shape. But he didn't know why. All he said was, I can tell you where it'll be and when it'll be there, and he was exceptionally accurate in that. And it took Newton to get a little bit further, and he said, an orbit's not just an ellipse. An orbit is what you do when you're mostly only affected by gravity. And so when you're in outer space, if you're in low Earth orbit, there's a few air molecules up there that are going to kind of slow you down because there is just a little bit of atmospheric drag way up there slowing you down. But if you're in deeper space, there's nothing but gravity acting on you. And so Newton says, an orbit is what you do when you're mostly only affected by gravity. And basically he came up with this formula. You saw that last month if you were here. And that is the formula for gravity, and that's how we know what it's going to do. And it turns out that predicts exactly elliptical orbits. And another way to think about it is, what is free fall? What happens 1 second after you jump out of an airplane, hopefully with a parachute?
I scream.
Yeah, you scream, okay. What are you feeling? Weightlessness. Are you feeling zero gravity? No. Gravity is very much acting on you 1 second after you jump out of an airplane, but what you're feeling is weightlessness, because really, weightlessness is just when there's nothing pushing up on you to counter you against gravity, okay? So I'm trying to kind of persuade you that an orbit is just the same thing as free fall. It's just in a repeating pattern where instead of hitting Earth, you come back around again. And so Newton's proposal was, what if we put a very, very powerful cannon on the top of a very tall mountain and we shot a cannonball? And so the first try, we had only so much energy, and we made it to point A, okay? But then we tried again, and we used a little bit more power. We got it to point B, and it wasn't until that third time when we got even more oomph behind that cannonball that we finally had enough energy to go all the way around the planet. And this would actually work if there wasn't atmospheric drag. Okay, so if you were on the moon, this would be possible. You could just get a cannonball going fast enough, and it'd be in low Earth orbit around the moon for quite some time before, because there's so little atmosphere to slow it down. Okay, and so Newton again says an orbit is what you do when you're mostly only affected by gravity. Now, is anyone in here, has anyone ever been in an airplane?
Yes.
Were you in orbit? Mylan, not in orbit. Why not?
There are other forces.
Yes, okay. So in an airplane, hopefully you've got wings and those are providing lift. And so, again, an orbit is not just flying. An orbit is when you're falling. You've got literally no control over anything besides just following the law of gravity and seeing where it takes you, okay? And that is, both C and D here are orbits because you had enough energy to keep going and there was nothing stopping you from going all the way around the planet, and you're just falling the whole way. Now, we're going to talk through the 6 numbers that define an orbit. I have a few helpers that might come up here in just a second, okay? And so what we're going to do is we're going to talk through some orbits. You can come on up. And so what we've got is we've got a hula hoop, okay? This is a circular orbit. And Isaac, will you give me one of the ellipses? Okay. All right. And Austin, will you hold the other ellipse because we're going to use that in a second. So this is a circle, and a circle has an eccentricity of 0, okay? And that's just a number that defines its shape. So 0 means it's not really, it's not flatter, it's not a flattened circle, it's not an ellipse per se, except it is an ellipse, it's just a special kind of ellipse that's the same height as it is wide, okay? But this is an eccentricity of 0, all right? Now, this is an eccentricity of about 0.8, okay? So it kind of got smushed. And then, also, can I have this one? All right, this one is an eccentricity of 0.95, okay? There we go. And thank you, Isaac. So here's the thing. When it comes to these shapes, you might, in your mind, think, well, surely the sun's at the center, right? But it's not like that. Will you hold this one just like this? Okay. It turns out that the focus of this ellipse is way out here, and the object, this happens to be the same shape as Halley's Comet, okay, with a eccentricity of 0.95. The object goes around it goes really fast by the sun because it's getting pulled in, and then it kind of slows down as it comes back out, stays here, and then it comes back in again. Austin, will you get one more? Okay. And so those are the shapes. So we've got an eccentricity of 0, 0.8, 0.95, and now all of a sudden when you get to something like this, you're talking an eccentricity of 1. So this is no longer an ellipse. It's still a conic section, if you remember back to math class, but this is a parabola, okay? And so this is what we just expect with an Oort cloud comet. You know, something that basically starts so far away, comes in, comes back out, and shoots back out, but it doesn't really ever come back, or if it does, it's not in a time scale that's easily measured. Thank you guys. You guys can sit down. And so these are some good helpers here, okay? And so that's the shape side of it. And question in the back, yeah?
So for Halley's Comet, when it's at the farthest point from the sun, is it still the sun's gravity that pulls it back?
Yes.
So it has that much reach and it just pulls it all the way back?
Yes, exactly. So that's the main difference between a periodic comet and sort of like a once-in-a-lifetime comet. So, you know, you'll hear about these comets and it'll be in the news, you know, this one's not coming back for 150,000 years. Well, why don't we just say it's not coming back? You know, like, it's sort of like one of those funny things of like, it's just so far out. And the funny thing is, so this is like your typical comet that you'll hear about, you know, it's not coming back for 50 or 100,000 years. it's actually kind of really hard to know what it'll do once it gets back out to the Oort cloud. Like maybe there's perturbations out there, what have you. So it's functionally a parabola. It like comes in from seemingly forever away, whips around the sun, and then slowly slows down as it comes out. But it does, we believe, stay bound to the solar system. It was in this outer reaches of the solar system, maybe 10,000 astronomical units away, and yet it was still bound to the sun, and it probably still is, but who knows if it's coming back in 50,000 years or 100,000 years. But Halley's Comet is periodic, and it's very clearly defined. Every 76 years it's going to come back, okay? One of the other things you'll notice how this one that is really eccentric really flies past the sun fast, and then it kind of really gets slow on the outside. That's just the nature of it has mostly potential energy when it's out there, and then it comes in and it gains its kinetic energy as it trades off that gravitational potential energy. All right, so size is next, okay? Let's just say this is Earth's orbit, and we'll give it, we'll call the distance from the sun to the Earth 1 astronomical unit. So this has a radius, right? Okay, it's a circle, and the radius is 1 astronomical unit. I don't know it in kilometers. I'm sorry, but because really we only use it in astronomical units for most parts. Okay, so this is a 1, and then if I had an orbit that was twice as large, okay, it would have a radius of 2 astronomical units, and that's its measure of its size. The trick is, though, what's the radius of this guy? Doesn't have one, does it? Okay, so it's kind of like, well, it's got a lot of radiuses. My math teacher would deduct points if I said that. But so it's got this kind of short version of the radius, it's got a long version of the radius, and we're just going to use the distance from the center to the farthest most point, and we'll call it semi-major axis, and that's right here. So from the center of the ellipse to either of the farthest away points is the semi-major axis, and that is what astronomers will use when it comes to how big is the orbit. The next thing we're going to talk about is tilt. And really, honestly, there's 6 numbers, but you really only need to pay attention to 3, okay? Size, shape, and then the last one is tilt, okay? If this is Earth's orbit, all right, and this is sort of its orbital plane, okay? And most of the other planets are all about in that same orbital plane. So we've got Mercury, we've got Venus, we've got Mars, we've got Jupiter, and we've got Saturn. No planets are up here, no planets down there. Occasionally you'll find an asteroid or a comet coming in from up here or down there, but all the planets are sort of in this plane. Well, the last thing that really defines an orbit is its tilt, okay? So if I was to take this, we'll call this a near-Earth object, because if you notice, it's intersecting with the Earth's orbit, okay? And so the tilt is just 0 degrees, 10 degrees, 20 degrees, 30, 40, 50, 60, 90, okay? And now those are the big 3 questions that you're trying to answer with an orbit. You're trying to answer what size, shape, and inclination. So eccentricity, semi-major axis, and inclination, they are typically E, A, and I is the letters that are used for that. And if you look at your handout, you'll kind of see that as the first 3 columns that are in green. Now, the blue columns are really not that interesting for the purpose of thinking about astronomical objects, but the green ones are really interesting, and that's the size, shape, and tilt. And I won't go into the other 3 except to answer. They just answer which one. So basically, it's like, well, what direction is the tilt? If I have this inclination of 20 degrees, is it in this direction? Is it in this direction? Is it in that direction? Okay. Could be any one of those. And then the other question is, which direction is that apogee or perigee if you're talking about Earth orbit, or aphelion or perihelion if you're talking about that with the sun? So what you're thinking about is these 3 questions just answer which one is it, and then the last question is, if I tell you that it's somewhere on here, and I fixed with the first 5 numbers that it's somewhere on this point, the last question is it here right now? Is it here right now? Or is it here right now? Where is it? How far is it along its path before it comes back to perihelion of being the closest to the central body? Okay? Questions about all that before we kind of look at this data table? Oh, one more thing. Okay. Puzzler. I always forget that I put in last-minute slides. Puzzler. This is the Memphis Astronomical Society logo. I know we love this logo. Are those orbits? I think they're orbits. Looks like there's a star there. Now, I was telling you earlier that elliptical orbits, the central body is over here, okay? Oh, man, are those... Can anyone save our logo? I'm sorry, Rick, I have to apologize in advance.
It's a binary. You can't see the other.
Yeah, can anyone save the... That's a good try. Yeah, that's right. It could be a binary star. Isaac, what do you think?
It could be an atom.
It could be an atom. Yep, that's right. There are atoms in space. We're going to have to get a new logo. Oh, no, Rick's going to be so mad at me. Actually, I can save our logo. Watch this. So those look like ellipses for you right here, right? But actually, we'll do this for the camera. Okay? So one of them is a circular orbit like this, and the other one's a circular orbit like this. And when you put them together, you get this picture. So this is actually a real orbit. It's two circular orbits that are at right angles to each other. Neither one of them is an elliptical orbit. Okay, so the logo can stay. All right. We're going to look at the data table just a little bit because there's just so many treasures in here. This is where you're going to have to rein me in because I could talk about this for 3 hours. We've got mostly, I've got in the first little section here, we've got the 8 planets. And if you look at the 8 planets, I want you to go over to the inclination, okay? Notice that the 8 planets, Mercury's a little bit of an oddball. It's kind of got a fairly steep inclination here. But most of them are, 7, 3, 0, 1.85, 31. Oh, sorry, that's not that one. Jupiter, Saturn, Uranus, and Neptune. So all those planets have an inclination that's low-ish, okay? As well as if you look at the eccentricity of these orbits, they're all more or less pretty close to circles, except, of course, Mercury. Mercury is the least circular flat orbit of the 8 planets, okay? Does anyone see anything with Pluto that looks a little bit different from the other 8 planets?
It's inclination.
Yeah, inclination's a little bit off. It's a little bit too high. The eccentricity is higher than any of the other planets. And the other interesting thing with Pluto is, while all the other planets have cleared out a part of their neighborhood, okay, Mercury owns the 0.38 area. Venus owns 0.7s. The Earth owns, give or take, say 30% on each one. They each own their zone, okay? Earth has cleared out 30% higher and 30% lower than its semi-major axis. Mars owns from, 1.2 to 1.9, something like that, okay? But what's the matter with Pluto? It's got some neighbors. So if you look at these other dwarf planets that were discovered, trans-Neptunian objects or Kuiper belt objects is what you'd call them, the reason Pluto got demoted is 1, 2, and 3, okay? It didn't clear out its neighborhood. It has a high-ish eccentricity, and it has a rather high inclination compared to the rest of the planets. So when you look at like this, it's like sort of blindingly obvious why it got demoted. If it's only for historical reasons that it was a planet for a while. It's like, okay, they didn't know about Haumea, Makemake, or Eris when they named Pluto a planet. And then once you know them, it's hard to maintain that it's somehow special. Okay, James Webb Space Telescope is interesting. It is 1/100th of an astronomical unit further from the sun, and yet, even though typically when you have a further out orbit, you have a longer orbital period, its orbital period stays exactly the same. Kind of crazy, but basically you can think about it as the sun and the Earth, because they're always lined up, and James Webb is out behind them. Okay? If here's the sun, here's the Earth, and James Webb is just a little bit further out, the Earth and the sun are pulling in the same direction, making James Webb think that it's orbiting a sun that's just a little bit heavier. And if it feels like it's orbiting a sun that's a little bit heavier than real, it can still do a 365-day orbit despite being 1.01 astronomical units. It should be like 380, except for that additional pull that the sun, that the Earth is doing to kind of keep it going 365. Okay. Anything else that you see that's interesting? Yeah, Rick.
Are you going to talk about what happens at the Lagrange points?
Yeah.
This orbits this way, and Lagrange points they orbit like this, which is why it's approximately 0 degrees in time.
Right, it's approximately, yeah. So basically at a Lagrangian point, you can't actually get it to park right at the Lagrangian point. It actually moves around the Lagrangian point, but it's still sort of interesting that you can get, it's all sort of approximate in that sense. And technically I'm sort of cheating. I don't think you can call the semi-major axis 1.01 if you use oscillating elements, but whatever. It's close enough for today. Last time I talked, I told you I was trying to find an asteroid. I found one. I only found one, and I will never find another one because the Rubin Observatory is going to get them all now, and there will be none left for me. So, but if you look at 2023 QJ3, I'm going to name it after my kids. I have 3 kids, so I have to use a portmanteau because I've only found one asteroid. Okay, so somehow we'll work out a portmanteau of their names. But the interesting thing that I found is like, how on earth did I find this thing? Well, it's kind of an oddball. It has an eccentricity that's rather high for the asteroid belt, as well as a pretty high inclination, and it's kind of small. So it was just luck of the draw. It still hadn't been found, and I aimed my telescope in the right direction at the right time, and I got one. Main belt asteroids is actually the replacement for the planet that should be between Mars and Jupiter. If you look at those semi-major axes, it's typically about 50% higher or double each time. So from Mercury to Venus, you're doubling it. From Venus to Earth, you're going 50% higher. From Earth to Mars, you're going 50% higher. From Jupiter to Saturn, double about. Saturn to Uranus, double. From Uranus to Neptune, about 50% higher. The oddball is, if you go straight from Mars to Jupiter, you're like doing a tripling, okay? There's a missing planet, okay? And the only reason we have an asteroid belt is that there's no planet that ended up there. If there was a planet there, we'd have no asteroid belt because it would just be kicking them all out to be trans-Neptunian objects or farther away. The only way we have a stable, beautiful 10 million object belt right there is because we're missing a planet there, okay? Let's talk just briefly about near-Earth objects. 2024 YR4, we're going to cover that at the end. That's the one that scared everyone, that kind of got up to a 3% chance of impact. We'll talk about that at the very end, but the interesting bit for you to see here is that it has a 4-year orbit about, which is why it snuck upon us exactly 8 years before the threatened impact. Because it was, it was just kind of slowly creeping up on us, catching up just a little bit every year. We see it, and it gives an 8-year warning because that 4 years is almost the same as 8, half of 8. The only other fun one that I like to talk about is 2020 SO. So occasionally we find, and actually I think we have somebody here who might know more about this than me, but an empty trash bag object is what it's called. So essentially the 2020 SO, it comes as a near-Earth object, it gets detected, and yet people are noticing there's something wrong with its orbit, okay? And what they're noticing is there's something besides gravity acting on it in a measurable way. And what they found was that it was lightweight, very, very lightweight. It can't be an asteroid. And it's getting pushed by the sun's solar radiation. Just those photons are pushing it in a measurably different way than if it was only gravity. And then they started scratching their heads. Okay, well, look at this orbit. Almost 1, almost 0, almost 0. Looks a lot like Earth, right? Well, that's because we made it, okay? 2020 SO was briefly designated as an asteroid before the astronomical community realized it had non-gravitational forces acting on it. There was something different. They rewound it, and they found it matched perfectly a launch in 1966 for the Surveyor 2 mission. And the way that it caught up with us eventually is it was catching up. It was like, lapping us, So if you got two people on a track and one's going just a little bit faster around the track, it was catching up by 7 days every year. And just by chance in 2020, it had just totally completed lapping us, and we caught it before it's back doing another lap. So 60 years from now, we might get another chance at it, okay? Any questions? Anybody see one on there that they find intriguing? We have time for about one question if there was something on there that was bugging you.
Peter, why does the inclination go more than 90 degrees?
Oh, that is a delightful question, okay? So they decided not to give one more number that we could have included is the direction. Is it clockwise or is it counterclockwise? So, but that'd be 7 numbers. That'd be too many. So what they did is they said, okay, everything's going in the same direction, unless we do 10 degree, 20 degree, 30 degree, 40 degree, 50 degree, 90 degree inclination, and we're just going to use from 90 back to 180 as the retrograde orbits. So a retrograde orbit is anything with an inclination higher than 90. And that was the way they said, well, how are we going to fit it into 6 numbers? Okay, well, instead of having one more number, which could either be positive 1 or negative 1, they just did it that way. Yeah, Nathan.
Fun, maybe historical reason.
Yeah.
You can't launch to retrograde. You have to launch interrograde, I guess it's called, and then gradually increase your inclination until you flip over the pole. It just takes too much fuel and power to launch to retrograde.
Fascinating. Okay, that's really interesting. Yeah. So which one was it that was retrograde? Right. Oh, great. We're going to get to 3i Atlas in a little bit, and it is going retrograde. It's also a little bit of an odd duck. So.
History of Voyager on there too.
Oh yeah. So that's super fun. Okay. So Voyager. So remember, Voyager is. I'll have a picture of it in just a second. But Voyager started out with an elliptical orbit about like this. Okay, so we launch it, we get it into an elliptical orbit like this, but we wanted it to go interstellar and go, visit some other stars somewhere. But we didn't have enough rocket fuel. It would have been cost prohibitive to get it all the way to interstellar velocity right away. And so it started with an eccentricity of 0.79, whipped past Jupiter and got an energy boost as it got a gravity assist, whipped past Saturn and got to an eccentricity of 3.72, and that's really trucking. So that is a fast man-made object. I believe, I think it's faster than Voyager 1. I can't remember. Faster than Voyager 2. I think Voyager 1 is maybe the faster of the two. But it's really interesting, and we'll probably cover 1 or 2 more if there's any more that you find interesting there. So I'm not the most knowledgeable on Earth orbit, but it's a talk on orbits. We got to talk about satellites just a little bit. You've got low Earth orbit right here, and then anyone have an idea what all these kind of dots are right as a ring? Well, we turned into Saturn, okay? We were envious, okay? That's all the geosynchronous satellites, okay? So this ring around the edge is all the satellites that are set up to have a 24-hour orbit. And you'll see an example geosynchronous satellite down here. It's at 42,000 kilometer semi-major axis. That's a lot higher than low Earth orbit. But because it has a 24-hour orbital period, it stays exactly above, more or less, the exact same spot on the equator all the time, which is why it's sort of like a really, really, really high cell tower. Imagine that we went to the equator and built a 40,000-foot high cell tower. Well, then it wouldn't be too hard from Memphis to be like, well, I'm just going to point my dish right there, and I'll get a solid signal all day, every day, because it functionally doesn't move. It's like there's a 40,000-kilometer high cell tower for you to aim your dish TV at. Because it's synced up. 24 hours of revolution, and the Earth spins the same amount of time, and that's how it stays put. What's that? That's right. You need it all the time. Okay. I have one more really odd orbit. Anyone have an idea what this one is? Isaac.
Interstellar.
Interstellar. Okay, great. I feel like my kids might know all the answers. They've heard me practicing. So this is coming through the solar system right now, okay? And this is an eccentricity of 6, and it is coming through fast. And the way to think about it is infinity that way, more or less, approximately infinity that way. A star kicked out an asteroid or kicked out a comet, okay? It probably got too close to their version of Jupiter. It got the gravity assist that it didn't want, and it was stuck in interstellar space for a very long time. And then it stumbles on the solar system, and it just kind of takes a slight left turn, okay? It only is going to make an 18-degree turn as it gets close to the sun, and then it's just going to keep on going. And that's kind of special because we've seen 3 interstellar objects so far. The first one was the slowest. Comes in like, let me make sure I'm doing this right, comes in like this and kind of makes a 45-degree turn. It got relatively close to the sun. It wasn't going too fast. The second one is 2I Borisov, discovered by someone who ground his own 65-centimeter mirror, f1.5. So this is somebody who's just like, telescope maker, and he works at an astronomical observatory all day. And then at night, he runs his own. So the second interstellar comet was a little bit faster. You can see that right here. And then the third one is a little bit faster yet. 58 kilometers per second is how fast it was going relative to the sun before it started feeling the sun's gravity. And now it's going faster because it's kind of gotten a little bit of an additional pull on the way in. I always say, if they keep on sending them faster, we're going to have trouble. So, I'm joking. There is one guy who consistently calls each one of these a spacecraft, and he works at Harvard. And I think he might be right. We never know. But Occam's razor says otherwise. Anyways, they keep on coming faster, and if we've gotten 3 so far, we're probably going to get up to 50 or 60 in about 10 years because the Rubin Observatory is going to make that possible. Oh my goodness, I'm so excited about the Rubin Observatory. So has anyone seen this video yet? Okay, we got 1, we got 2. Well, okay, great. This is a super cool video. The Rubin Observatory is kind of a wonder of the world sort of a telescope. It's sort of right up there with Hubble and James Webb. It happens to be on Earth. It has a very wide field of view, an exceptionally large array of CCD, I think it's CMOS, but an exceptionally large camera array, and it is just going to find so many things. We're going to watch this really briefly. Okay, there we go. Each one of those points of light is an asteroid. And now, day 1, 989 discoveries. Day 2, 1355, 1358, 1638, and 1793, and I think it gets to 2104 by the end. And that was only 10 hours of exposure time that it got 2,000 asteroids. And look how big of a chunk of the asteroid belt it was looking at. So just that little narrow window, and it got 2,000 new asteroids. Very exciting telescope, and it's basically geared towards transient events. So its goal is, let's find supernovas, let's find anything that got brighter or dimmer or moved. And asteroids is one of those, and it's gonna kind of crack that open for us. The other cool thing is it's going to find kind of the remainder of the scary near-Earth objects probably over the next 10 years. A lot of NSF and Department of Energy funding, and it's just kind of one of those reminders of you can't do cool stuff without money. And so, in the time that we're in, I'm like, all right, may as well make that case. Keep funding science. It shouldn't all go away, okay? Enough on that. Math is beautiful. 6 numbers. I was feeling so confident when I finally figured out the 6 numbers, and I'm playing, and I'm like, I'm a self-taught orbit guy. And I finally download a new orbit database, and I'm utterly lost. Because it doesn't have my 6 numbers that I'm used to. And so it turns out, I slowly learned as I stared at this thing and Googled, okay, they've got different numbers in here. And so it turns out that you're allowed to substitute the pericenter distance, or you could substitute the apogee or the aphelion distance if you wanted to, instead of the semi-major axis. And it turns out that as long as you know the eccentricity, you can back from the pericenter distance to the semi-major axis. Then all of a sudden there's these two that can also be substituted. And I slowly began to realize, oh my goodness, they do this thing, but there's always 6 columns. That is so cool. And what this reminds me of is if we're right here and I tell you, treasure chest, $1 million worth of prize, 1 mile north and 1 mile east. Go, everyone go. All right, who's going to get there fastest? What's your strategy? Hypotenuse, okay. So you're going to get out your compass, you're going to set it to what 2 numbers? Angle of 45 degrees, right? And 1.414 miles, and you're going to get there first while all the others are still sort of somewhere over here. How many numbers did it take you to get there? 2 numbers. If you started with 2 numbers, you can't find a place on a map without 2 numbers. You got to go how much up and how much over, or how many degrees and how far over. 2 numbers, 2 numbers. It turns out the exact same thing is true with orbits. There's one more that I just absolutely love. If I tell you exactly where an object is in three dimensions, x, y, and z, and I tell you exactly how fast it's moving, could you calculate its orbit?
Yes.
6 numbers. It's getting really close, isn't it? Think about it back to the cannon on the top of the mountain. If you knew exactly where it was starting and exactly how fast it was going, would that be enough for you to know if it was going to orbit?
Yeah.
I think so. It turns out this is exactly the same. These 6 numbers can be converted in a millisecond to those 6 numbers and back and forth again. There are literally hundreds of different orbital definitions, and they all have 6 numbers. And I only know 2 of them. So I Googled the rest, and there's 6, 10. You could literally add it up. You could literally invent another one tonight. As long as you got 6 numbers, you can define an orbit. And so as I learned more and more about this, different mathematical disciplines, different groups doing orbits are going to find their favorite 6 numbers. It's always 6 numbers. And it kind of reminds me, Galileo said, mathematics is the language in which God wrote the universe. And I'm like, it's beautiful. I like it, okay? And so kind of thinking more about the 6 numbers and the beauty of it all, I have a scatter plot. So this is a selection of asteroid orbits that are pretty well known. And we took 2 of the 3 numbers, and we made them the 2 axes. So semi-major axis is on the x-axis, and on the y-axis is inclination. And you'd expect potentially that this would just be all diffuse, all kind of spread out. It's an asteroid belt. It's all spread out, isn't it, right? That's what we think of. It's all spread out through there. And yet it's kind of clumpy. And this is a puzzle at first, okay, until you notice, all right, the biggest asteroid in the asteroid belt, number 1, Ceres, has this cloud around it. Okay, that's kind of puzzling, all right. There's another big one out here that has a kind of a whole bunch of things right around its orbital elements. And what we slowly realized is that there are asteroid families, okay? And this is sort of the known asteroid families when we pull out all the ones that we don't know who they belong to, okay? So much of the asteroid belt doesn't have a family, but if you just take out this one that doesn't have a family, and that one that doesn't have a family, and that one that doesn't have a family, and you just look at the families, you get something really beautiful like this, all right? Now, I have a puzzle for you. Which is the oldest family? Flora, Vesta, Maria, Hofmeister, and Veritas. And which is the youngest?
The youngest is Veritas.
I think you're onto something. Why? Why would you say that?
It's smaller and it's had less time to spread out.
That's right. Okay, so typically these asteroid families, there was some sort of a cataclysmic event, an impact, something that happened that was, two large bodies hit, and they just spray smaller things. Okay, and they've all kind of got the same orbit, all right, but they're sort of spreading out over time because the longer they go, the more they have time to get perturbed by the planets. And so you're absolutely right. Okay, the two youngest ones are the small ones, all right. And the ones that are more spread out are older. And so it kind of happens to be that we can see backwards in the solar system's history because of asteroid families. You can kind of rewind it. And, it's rough. The Maria family is somewhere between 1.5 and 2 billion years old. But, you kind of get the sense of these things by seeing how much time would it take for them to spread out by that much. Okay, well, that's how old the family is. All right. I'm not the best at Earth orbits, but I do kind of like. I wanted to work at NASA when I was a kid, and so I wanted to share this one just as a brief kind of like how do orbits work in Earth, and how do we get a satellite to where it goes. And I think there's people that may well do a better job of this than me at some future meeting. But basically, you got launch, and then you got this parking orbit right down here. And essentially, when I was a kid and I was thinking about orbits, I'd say, well, I'm trying to get over to right here, so maybe I'll fire my engine right here when I'm moving in that direction. It doesn't work that way. You fire your engine to change where you'll be on the very opposite side of your orbit. So after your initial parking orbit, that SpaceX drops you off in your parking orbit, and then either they or you will do your burns to get where you need to be with that second stage engine. The first burn pushes your apogee out further, and your second burn makes it circular again. All right, and that's basically how high up is part of how you're going to determine how much fuel you need, because you're going to need more energy to get further away from Earth. Speaking of Voyager 1 and Voyager 2, this is just a picture of those gravity assists that they got that got them going fast enough to leave the solar system. And this is kind of a fun picture of just each time it encountered a giant planet, what its energy did. So after it encountered Jupiter, got a lot more energy, and that's when it first got to interstellar speed. Encountered Saturn, and now it's going to get where it's going faster. I'm not sure if it's in a hurry, but Uranus got a little bit further. It lost a little energy around Neptune, and throughout it, as soon as it got past Jupiter, it was able to get out of Earth's gravity because of that gravity assist. It's time to see an asteroid be born. Okay, this is the closest I'm going to get to the county fair. Come right over here. You can see an asteroid born here today. Okay, now. Basically, I've submitted one, and we're going to see if it has a name in just a second. So right before you got here, I submitted an asteroid, and we're going to see, and you can be there, at the end you can write on your t-shirt, I was there when 2025X, whatever it is, was born, okay? Here's how it works, though. I like to think about it as there's like a billion-piece puzzle, and every day there's new pieces being shaken out as the observatories point to the sky, say there was a moving object. Now, there's 495 million observations on record, and most of them we know what they belong to. This observation, that observation, it belongs to this object or that object. So only 9 of the 495 are still homeless. We don't know what they belong to, and then that leads to this problem called the linking problem. You're trying to take all those and figure out which ones go with which, all right? And there's an isolated tracklet file, which is basically just a file of all the observations among this 9 million that the Minor Planet Center has, and they don't yet know which one goes with which, okay? And the linking problem is, can we figure out which goes with which? So, I'm sure Rhodes wouldn't mind if we drew on the, no, I'm joking, we drew on the screen. Anyone want to draw a parabola or something curvy that connects the only 3 points that belong to this asteroid? Which 3? Now, this is sort of like this, okay, over here. I drew this one a little bit easier. I have a parabola and a line. Could you point them out if, All right. Yes, you could. Okay. So you could say, I see it. I see it. There's a parabola here. There's a line. And that's all this is you're basically trying to figure out, can I find 5 or 6 observations that are clearly part of, that I could give 6 numbers to and it matches perfectly, or more or less perfectly. So we've got all these observations in April to May 2025. I won't make you guess because you could literally try 1,000 different permutations and they'd probably all be wrong. Here it is, okay? So this observation right here, and this observation right here, and this observation right here are an asteroid. This one is not. It might look like it is, and it does not belong. And the reason we know it doesn't belong is because if I could zoom in for you, you'd see that the shape right there, we always get 2 or 3 observations from a given night. So the 3 observations are something like this. What we want them to be is, so if you zoomed in far enough on either of these, you'd see that the 3 points are just perfect, okay? And you want them to be within, like, say, a half an arc second for it to fit. And so we have found an asteroid. What I did is I then, after I got those 3, I wouldn't submit this normally because this one is just a little bit too far out. And, you know, you start wondering, am I just piecing together, is this a conspiracy theory or is this, you know, a real object? Okay. This one being so far away from the other 2 made me skeptical. So then I looked in other years and I found some observations in other years and I was able to piece it together. So I'm certain it's an asteroid. And I submitted it right before you got here. We'll see if it has a name. Here it's in the outer asteroid belt, sort of that 3.13. It's relatively circular, and it's got a 28-degree inclination. Let's see if it's got a name. All right, drum roll, please. You were there when 2025 HH50 and 2025 HJ50 were born, okay? So you've seen an asteroid born. It's kind of fun just because I kind of get a lot of joy from sending something in and getting it acknowledged like an hour later. It's really, you know, it's a fun game to play. When you get to submit something, they have these live pipelines running all day and night, and if you submit something, they're going to process it immediately and tell you if you were right. Last, just human interest story that's kind of fun. It takes a village to do some of this fun stuff. There's I found this object, which is 2007 HE4, and I had a machine learning model that I trained to find asteroids that were probably actually comets. And this one was sort of at like the 99.9% sure it's a comet, but I can't find any pictures of it. So it's like the machine learning model, it's like AI is a funny thing. It can be certain of something, but nobody takes the AI model is certain of something as truth. They want to see a tail on it. So I posted it on a comets mailing list, and I got this back from a guy that I know. Peter is in the UK, and he is using his telescope almost all the time for near-Earth objects, but he'll also do anything that's of note. He got a picture of it back in 2007, and it's sort of a marginal tail. Do you see just a little bit of a tailward, a little bit of a bias in the left to left here? That is the tiniest tail you ever saw on a comet. He didn't report it as a comet because it wasn't clear cut, and a lot of people didn't report it as comets, even though they got a picture, and it's kind of on the edge. Now this is the fun part. There's a guy. His name is Mike Meyer, if I'm pronouncing that correctly. He is the world expert in lost comets, historical comets. He's written a multi-volume set of the history of comets through, all of collected history. A few days later, he says, I know what it is. So it's 1894 F1. It hasn't been seen since 1894, and he just kind of brilliantly, what did he do? He lined up these numbers. And so he looks at it. This is the orbital elements that I had found for this object. He finds in his list of all these objects that might indeed be interesting, that are long gone. He kind of sees that there's a correlation, runs it through his orbit fitter, tries and tries and tries until he gets a perfect fit after playing with the parameters. The interesting thing is the semi-major axis is meaningfully different between the two, even though it is the same object. And so what happened with that is that because now we've seen it 2 different times, 1894 and 2007, and because on both of them, they saw a tail on it, it now is periodic comet 489. And I was just kind of curious. I was making this slide, not expecting anything. I checked, and it's like literally visible for the first time since 2007, starting a week ago. So if you wanted to get out your telescope, and if you can get to mag 20.5 or so, you can.
See that, Tim? Because that's impressive.
Yeah. Well, I use remote telescopes to do that sort of thing. But you could get it, and it will get to magnitude 17 in January. This is kind of its evolution. It kind of got close to Jupiter 2 times. Each time it got perturbed because it got a little bit too close. And so this time it got too close to Jupiter, and it kind of got a boost to a higher orbit, okay, or a longer orbit, and then it got another boost here. And that is kind of the brilliance of him lining these two up. I would have looked at that and said, can't be the same object. 4.42 is nowhere near 3.47. But he realized that, this is a Jupiter family comet. Jupiter family comets are constantly getting a little bit too close to Jupiter, changing their orbit, and it is indeed the same one. If you want to watch that 130-year history on your phone, you can always snap a picture of the QR code and hit play and kind of watch this thing go around. The fun part is, if you do this, and you can do it at home, you can do it here, I don't care, you will see 2 major events where the orbit changes significantly. Got close to Jupiter, and the whole thing changes. And those line up perfectly with kind of this graph of the orbital evolution. This is what it looks like right now. So the reason it's just kind of becoming visible now is that it's coming in. It's a comet, so it doesn't really start gassing, getting brighter until it gets closer to the sun. It's on the way in, all right? We're on the way around, and like a month ago, you couldn't have seen it because it was too close to the sun, because this was Earth, that was the sun, and there was Comet Denning. It was just a little bit too close, but now you can see it in the morning sky because after the sun sets, you can kind of see over there. And if you fast forward a few more weeks, hopefully you can catch it. So one of these days, I'm going to try one of my remote telescopes and see if I can see something from 131 years ago. We're going to talk just briefly about near-Earth objects, and then we have a little bit of time for questions. Anyone here follow the near-Earth asteroid that was kind of exciting a few months back? Raise your hand if you watched the news. Yeah, pretty interesting. So. 2024 YR4 is the name of this object, and it's 50 to 70 meter object. So why were people so excited? Well, this is all the objects that we're aware of that have a non-zero chance of impacting Earth in the next 100 years. Okay, most of them are something like 1 in a million to 1 in a billion chance of actually hitting Earth. But astronomers are careful people. They want to keep track of those really, really small probabilities, and they've got some amazing techniques for figuring out, well, this one's a 1 in a million and this one's a 1 in a billion. And it's tricky, but they can do it. The reason why 2024 YR4 really kind of got on people's radars is because it's bigger. So if you look at the diameter of each circle, that tells you how large the object is. So it's kind of a bigger object, all right? It's 50 to 70 meters, kind of a little bit more threatening because it's larger. And it just, when it gets up to less than a 1 in 100 or greater than a 1 in 100 chance, that's when you kind of start paying attention. So it's still possibly going to hit someday, but it's like just one of many different possible impacts. And by and large, all of these do not matter. Like all of those, you actually have a higher chance of getting, struck by lightning while being eaten by an alligator. So, it's one of those things of we keep track of it because it's interesting and because there potentially are a few more really scary objects out there that need to be found. In fact, like 6 months ago, I found one that was, I think it was 300 meters. And I found it in the isolated tracklet file, and it did a very close pass, and it's not going to hit anytime in the next 100 years. But it was like, oh wow, okay. Whenever you see that flash, across the screen of like submitting near-Earth objects, you're like, I hope I don't end up famous for the wrong reason. So anyways, there are still some monsters out there, and we're finding monsters every day. But by and large, space is big, and there's nothing really to worry about. And it'll probably be another 10, 20 years until we have another 2024 YR4 that merits that escalated attention and attention to detail there. Also, just interesting. There's some really big objects with 1 in a billion chances of hitting in the next few years. So it's what that means is it means almost nothing because 1 in a billion is so small. So there are some websites that like to create some clickbait. There's now a 1 in a billion chance that an Earth-ending asteroid is going. It just sort of means nothing.
As me winning the lottery.
Yeah.
Well, somebody's going to win the lottery.
That's right. That's right. So let's see here. If you look, the other two interesting near-Earth objects on your piece of paper are Bennu and Apophis. The exciting thing about Apophis is that it's going to be really bright pretty soon here. So actually the last slide of the day will highlight how bright that's going to be. But there's some kind of exciting close approaches coming with big objects that once were threatening. We watched them long enough and they kind of fell off the radar. So that's why you do it. You just watch it because it's eventually going to fall off the radar and you just have to stick with it. And you hope for not that 1 in 30 chance that it stays on the radar. This is one of my favorite plots. The European Space Agency has some beautiful plotting people. I love this 4-dimensional chart. 4 dimensions, size, color, X and Y. Okay, beautiful. They also do this really cool thing with polar plots like this, where time is on the exterior of it, and the blue line is Earth's radius, and each of these is a close approach or an impact. So each close approach is out here, kind of got closer than the geostationary ring. So geostationary satellites are this dotted green line. The Earth's surface is the blue line. Anything inside the surface is a collision. Anything out here is, wow, that was uncomfortably close, but and so here's the really fun thing is just to watch the progress of big telescopes figuring out how to do a good survey and doing their job. In all of 2005 to 2006, nothing. Okay, 2005 or 2006 to 7, nothing. Now, 2008, we got 3 close approaches within the geostationary ring. Let's fast forward to 2016, and there's like 6 or 7, and now we're getting 10 or 15 in a single year that we're detecting, following, tracking as they come closer than the geostationary ring, and most of these are very small. The 11 that have hit after being detected are all kind of small, but they put on a pretty cool show. And the Rubin Observatory is going to make the number of those that we find in advance much higher, and I'm kind of looking forward to buying a plane flight to watch some of these shows, because it's like usually a fireball is something that you just see because you were out at night and it caught your attention in the periphery of your vision, and you're like, what was that? And it might happen once a decade, a really big fireball. But now you'll be able to buy tickets and go see some amazing, 3-meter objects, nothing to worry about, but they'll put on a good show. Speaking of good shows, Apophis is going to be a naked eye object in 2029. So they're kind of calling this 3 or 4 years here of, I don't know what they're calling it, but they're calling it something, because this is exceptional to have 4 almost naked eye objects in as many years. So these are ones that you'll be able to see with binoculars pretty easily. You could go out with your binoculars, you could look at it, you could go inside, wait 10 minutes and look at it again, and it'll be in a new location. You'll literally be able to watch it move across the sky because near-Earth objects are fast.
Is that lunar distance?
Yes, lunar distance, yep. So this one is the one that would have been all over the news, say 10 or 15, 20 years ago. I don't know how long ago, But Apophis was the most threatening asteroid known for a very long time, till they finally got enough observations to realize it wasn't going to hit. It was just going to get really, really close. So now we're certain it won't hit, but it's big, as you can see. That's causing a lot of destruction if it hits, but it's big, and we're certain that it won't come any closer than 0.1 lunar distances. But at 0.1 lunar distances, you'll have your once-in-a-lifetime chance to see a naked-eye asteroid. Okay, so don't miss it if you can. The last thing I'll leave you with is if you just like thinking about this stuff, there's only one person that you need to follow. This guy Tony Dunn is amazing. He's kind of the only reason I still go on Twitter. X, sorry, it's all the same thing, right? He does beautiful things, and he's always posting another interesting picture of this is what it looks like to ride along this near-Earth asteroid as it comes closer than the geostationary ring, and you get to see how close it got to Earth. Every time there's an impactor, he'll have this video of it kind of coming in, and bam, where it hits. So I strongly recommend, if you kind of find this stuff beautiful, just follow him, and you'll see interesting things on his page all the time, like this one. So this is the solar system cruising through the galaxy, okay? Because the sun has its own velocity, and we're just all moving around the sun, but the sun is moving through the galaxy, so that's kind of what it all traces out. Thanks for sticking with me as we kind of did a bunch of math and numbers, and we've kind of got 5-10 minutes for any questions, either something we talked about, something that's on your mind, or an interesting number that you see on your handout. Yeah.
I got a weird question.
Yeah.
I was meteorite editor for a long time.
Say it again.
I was meteorite editor for a long time.
Oh yeah.
And then when I had an article in there called The Planets.
Yeah.
Month, and I was using BASIC. And I went back and got my astrophysics and astronomy textbooks I used here as a student.
Yeah.
And I plugged them into the computer, and it worked. But there was one drawback to it, and I never figured it out. You might tell me. For the outer planets, for the inner planets, it stayed the same fine all year. But for the outer planets, from Saturn or Mars on out, after September the 1st, it was 12 hours off. And I had to add 12 hours to the rise and set times.
Gosh, that's tricky.
What it was.
That's wild. That's wild. I don't know that.
Add 12 hours after September 1st.
Yeah.
They were correct.
Yeah. I don't know.
January 1st, they went back to everybody.
Yeah. That reminds me, my first archival observation I submitted, and they politely replied that it was during daylight that I submitted because I had a 12-hour offset. So, I submit these archival observations, and they're like, well, in Hawaii at that time it was broad daylight, so, try again. I don't know. That's wild. It shouldn't be like that. Yeah.
I didn't think it should either. But
Yeah.
like I say, once I figured it out,
Yeah.
I got the right data into the meteorite.
Yeah. There you
I
go.
was using BASIC. I don't know if you ever saw this.
I did. It's been a long time. Yeah, for sure.
At first, I was printing meteorite on tractor trailer.
Really?
Yeah.
That's cool.
That's cool.
Rick remembers those.
Any other questions? Something that you're interested in? Did the meteorite make it all the way around? Did you guys get to see it? Okay.
Yeah, it's
That's
lost.
good. It's lost. No, he's got it. Yeah, Steve.
Do we know what is the greatest probability in one of these interstellar collisions or the collision orbits we know about? What is the greatest probability?
Yeah, so it's, if you look at it, there's a few that are like right at that 1 in 200, 1 in 300 range. So you kind of got, this one is sort of 1 in 200, 1 in 300, that one's 1 in 200 to 1 in 300. So there's a few objects that are up there, but they're not super threatening, okay? One thing is they're super far away. So we have plenty of time to firm up the orbit and know for sure if it'll hit. And the second thing is they're, I don't know, 13 meters, 17 meters. And while that is worth evacuating, if it's going to hit a city, that will like break glass across the city, and people will get injured because they came to the window to see the fancy light, and then the window breaks and shatters in their face. So it's like there's some 1 in 200s, 1 in 300s. They're so far away that once we watch them, by then we'll know, almost certainly if it's a 1 in 200 chance today, we're going to watch it, and 199 of such objects are going to get their risk entirely retired before the date it comes. So it's very, very low probability.
Interstellar objects,
yeah.
You're not going to have as much observation time
right.
beforehand to know. So bottom line is, if we get hit by an interstellar object,
yeah.
it's just our time.
yeah. Space is big. That's the good reminder there. Yeah.
One of my favorite doomsday scenarios is the rogue neutron star cruising through our galaxy. We're all screwed.
Yeah.
Even if you see it coming, like, okay, that's basically a black hole coming through. Like,
that's right.
We're in a lot of trouble.
Is it expected that the Rubin telescope will find lots of potential collisions, or is it unlikely to?
Yes. So this is like, so if we know 30,000 near-Earth objects right now, this is the 1,800 or so that are on the European Space Agency's risk list. Okay, so by just logic, if your population of known objects goes up, the population of possible impactors is going to go up. And I have a slide. I hit it, but okay. So I expected to go way over, so I hid all these slides that are actually kind of fun. So if you look at this one, this is the way it worked with 2024 YR4, is that it had a wide, at first it has an absolutely enormous uncertainty of how close it'll get to Earth. Oh, well, it's kind of got a 1 in 1,000 chance we should follow up on it. Oh, shoot, it shrank to 1 in 500 chance. We should give it more attention. Okay, shoot, it shrank to 1 in 200 chance. We should give it more attention. Oh, shoot, it shrank to a 1 in 30 chance. We should give it more attention. And the way these things work is that the calculated probability of impact always goes up at first. Not always, but usually, because you're shrinking your error bars, and thereby the width of the Earth, which is the width of this gray bar, takes up a larger chunk of your narrowing bell curve. And then, right at the end, once you get narrower and narrower, okay, now it's excluded. We're sure it's not going to hit. Okay, so I actually heard a very smart statistician with a podcast commenting on the astronomers don't know anything. He was talking about it on This Day or so. These astronomers don't know anything. They downgraded it from a 3% chance to a 0% chance in a week. How'd they do that? Well, he just hadn't actually looked at the probability. It really was a 3% chance when this is the bell curve. Okay, this is the normal, this kind of the standard error of what we expect. And so this is taking up a big chunk of that bell curve, and now it's taking up almost none of it, a few days later as you shrink that. So what will happen is that Rubin, by finding a large population of new objects, most of those objects are uncertain at first. So, many of them will end up on this list until we follow up, and eventually shrink the uncertainty to the point where, it's not concerning. So, yes, probably the people who make clickbait about asteroids are going to have a fruitful 2 or 3 years, as they get all these scientifically true new object names that they can say, there's a 1 in 1,000 chance it's a planet killer, but 1 in 1,000 turns into 999% of the time. And so, we should expect that, in a year, this will have more than 1,800 objects on it, and in 10 years it'll have more than that. But by and large, if I give this talk in 10 years, it has a very high chance of nothing besides a few light shows on the horizon.
I don't know how.
Yeah.
I forget how often Barry Rubin is supposed to image the entire sky how often it takes for him to do that, but it's not very long.
Yeah.
And while we'll see the numbers of new before named asteroids show up in the Vera Rubin data,
Yeah.
it'll also be repeated enough that how fast they can narrow in on the orbits will happen a lot quicker.
Exactly.
So this may explode for a while, but then reduce down quickly as they get enough observations on every one of these objects to understand its true orbit.
Where is Rubin?
Rubin, Chile. Yeah, it's in Chile. Yep. And I'm just so thankful they finished it before kind of budget stuff kind of got tight and what have you, because it's ready to go. And now all that needs to be paid is salaries and electric bills and maintenance. But yeah, it's really ready. Yeah.
It was I think in the first 10 hours of operations, they'd seen thousands of new objects.
Exactly. Yeah.
7 days of operation, it's just awesome. So.
Yep.
Very cool.
It'll be very exciting.
Anything else? Any more questions? Peter, thank you very much.
You're welcome.
So you get to be the first to receive our very cool, and you too can have one of these. You get up here and make a presentation. Okay. Featured speaker coffee mug with the very cool MAS orbital logo on the back.
All right.
Thank you so much.
2 circular orbits. Thank you. This is a joy. Thank you.
Thank you. That's all. If you want to, yes.
Yeah.
Just a random idea. So, since there's no planet there, so you have all those asteroids, would it be possible to push a couple asteroids into each other and make a new planet?
No, that's very difficult. Only in the early solar system was that possible. Right now, it's maybe pretty difficult. Yeah. But some people are talking about mining them, so yeah, we'll see.
So this is the official end of the meeting. Feel free to stick around and visit for a few minutes if you like and socialize. Thank you all for coming out, and have a good evening.